Okay, while I was chatting, I forgot to share my screen. How rude of me. I'm so sorry. So let me share my screen. I hope we got that there. I'm going to put that there. I'm going to put the chat in here. Okay, let's move on. So we are 42 tutoring and we are looking at projectile motion. Okay, so when I'm talking about projectile motion, what I'm talking about is moving things in the Earth's gravitational field. Okay, that's what all I'm going to do. Move something in the Earth's gravitational field. And there are two things that you need to know. And if you need to know them, then everything is straightforward. Okay, but you got to really think carefully about what's going on. You've got to be super clear, and you've got to be able to apply your knowledge, which you learned in year 10, to projectile motion. Okay, so you've got to be really careful. So, gone through all the specifications, we're going to cover everything that everybody needs to know, including IB, but there's nobody doing IB out there. But that is really good fun. Okay, so let's have a start. Now, I noticed that when I saw this Shaun the Sheepy thing, I was really interested in how the animators actually animate it because there is some serious maths going on there. Now, it turns out that I used to teach this man's children. So this is Peter Lord, the Nobel Prize winning, oh my goodness, the Oscar winning animator. And in one parents' evening, I said, Peter, okay, let's not beat around the bush here. How on earth do you, when you are animating Gromit falling, how do you make it look good? How do you make it look realistic? Because obviously, whenever you do that sort of thing, you are thinking about A-level physics. You must be thinking about A-level physics. So each time you put your little plasticine model, click, then you move it, click, then you move it again, click, and move it again, click. How on earth do you make it look absolutely perfect, as if Gromit is actually falling? I said, you must know those equations. You must have studied A-level physics and got a very good mark to be able to understand what you're doing to make it look good. So there are the equations, not forgetting the GCSE one as well. And he looked at me as if I was a complete idiot. And he said, no, I have no idea what you're talking about. He just does it by eye. How he does that, I don't know. I'm sure it will be much more, it'll be easier, I think, if you actually calculated it. So the people who make these games, okay, if there's any computer game like this where things are falling or moving, then there is some serious physics and maths going on there. Okay, I was just chatting to Anti-Man earlier. So there's somebody, I don't know who it is, from Frozen. I know that. I don't know her name. Could be Anna. I don't know. She's jumping. I could make a blob jump and make it look effective. But she has got a coat which is blowing in the air. So there must be, for her, a resistive force. And for the other one, as she's falling vertically through the leaves. Now, that resistive force messes things up. Now, I have seen questions in GCSE, in A-level physics, where you're not expected to solve the equation that you can derive from these sort of scenarios, but it says something like, can you please draw the trajectory of the object when you do not ignore air resistance? Because lots of these questions say ignore air resistance. Air resistance is negligible, which is great. I like that. But if air resistance is not negligible, so you might be playing badminton with a ball with a huge amount of air resistance. The shuttlecock is a ball with feathers sticking out the back. So there is a lot of wind resistance there. Or tennis, you've got a fluffy ball. There is a lot of air resistance going on with that tennis ball, which enables it to do clever swervy things. But still, the physics is slightly more important. Right. Let me just remind you, I'm sure you've all done that. Whenever you do your stickman pivot animation-y thing, the first thing people do is to make it look as if it's falling, and it's rubbish. It's rubbish because there are some things that you have not remembered. Now, if in your A-level exam you remember these things, you know how to use these things, then you'll be all right. Now, the reason I put that there is because we did this in the maths thing, the maths for physics thing. Why isn't this working? The maths for physics thing. But I'm just going to briefly show you why they have said that. Okay, so this is where they use it. It is that. That is the quadratic equation. Now, to prove that that is a quadratic equation in t, what I'm going to do is s equals ut plus a half a t squared. I'm going to rearrange that to be a half a d squared plus ut minus s equals 0. Now, that is a quadratic in t. We have got a term with t squared in it, then t, and then a constant like that. Okay, so that is of the form ax squared plus bx plus c is equal 0, which is your standard quadratic equation. You've got to get it into that form before you can apply that thing. Okay, now that thing tells you, now this annoys me a lot, annoys me more than it should. In your quadratic equation, the constant, which they call a, is actually a half a, if you see what I mean. For the quadratic equation, the standard quadratic equation, ax squared plus bx plus c, the coefficient in front of the x squared, the a, is, for the physics equation, a half the acceleration a. Similarly, b is the initial velocity u, and c is minus s, which is the distance traveled. Okay, when you suss that, then you'll be able to put that into the formula there, so you know what a, b, and c are. Okay, not easy. I'm not going to lie. That's the hardest thing that they might ask you to do. No, they can ask you harder things, but that is pretty darn tricky. And the question with that in, if you remember it, is that one. Okay, that's a nice one because you need to use the quadratic equation to find out how far the long jumper jumps if he lands 50 centimeters. His center of gravity is 50 centimeters lower than where he took off. Okay, you can see that it is, because his center of gravity is about there when he takes off, and is about down there when he lands. So we've got a bit of an S thing going on there. Okay, but more of that later. More of that later when we do maths with physics. So that's what you need to know about that thing there. You need your equations of motion. Now let's make a start. Now let's make a start. First thing we need to do is to make absolutely sure we know what we're talking about. So we've got Newton's laws. Okay, we know what they are. You can rattle those off until you're blue in the face. You know exactly what they mean. But what I want to do is to pick out of those three laws some interesting points. The first one is that. Okay? Unless a force acts on it. And that was another one. The acceleration is in the same direction as the force. Okay, those are the two things that you really need to have clear in your head when you do projectile motion questions. Okay, there are some other things that you need to know as well. Okay, I wonder if you can find out if you know what they are. Right. Let's go back to Newton's laws and think about the force. So let's think about resolving forces. I can think about the left-hand scenario where there is a ball which is being forced in that direction. Okay, I can resolve that force at an angle as that force and then that force, because the resultant of those forces, which I should have drawn with the ruler, so I'm going to do it now. The resultant of those forces is that. Okay, that is the resultant of that force. Now, if we think about Newton's law, okay, 1 and 2, is that going to be in equilibrium? No, because there is a force acting on it. Okay, so let's think about the second law. So if there's a force acting on it, it is going to accelerate. I have now split it into two perpendicular components. That ball is going to accelerate in that direction because FH, the horizontal force, is acting on it. It is also going to accelerate in that direction because there is a vertical force acting on it. Easy so far. Now look at the right-hand side. We have simply got a ball which has got a force acting downwards. That force is called its weight and acts downwards. Now I'm going to resolve that force horizontally and vertically, just like I did for the first one. So I'm going to, first of all, with a ruler, because it's going to be important. So that is there it is. That is the vertical component of the velocity. Rubbish. The vertical component of the force. Okay, so here is my force over here. That's it. And that is the vertical component of the force. Now, what is the horizontal component of the force? Well, there isn't one. There is no horizontal component of the force. Okay, now that's an important phrase. There is no horizontal component of the force. Okay, because sometimes the mark schemes, when you get to practice these things, have a look at the mark schemes, because quite often there is one mark for you saying that there is no component of. Okay, so when something goes around a circle, there is no component of in the certain direction, but more of that with circular motion. But for this one, projectile motion, when something is simply in the Earth's gravitational field, okay, like that, then there is a force acting on it called its weight. It is acting downwards. There is no component of that force acting horizontally. Therefore, it will not accelerate horizontally. That's important. It will not accelerate horizontally. If we start off by pushing it horizontally, whoopee-doos, that's great. That velocity is going to stay the same. It is not going to change because there is no component of the force in the horizontal direction. So that's what we need to know. And that's what we've crystallized from our Newton's laws. Okay, now let's have a think about what are these vectors that I'm talking about. So here is my thing in the air again. What I'm going to do is I'm going to make it move in those directions. So those are its velocities. I've done them in red. Those vectors are the velocities. Now, what I'm going to do is I'm going to add to those in green the acceleration. Okay? The force is acting what? The force is acting downwards. Therefore, the thing is going to accelerate downwards like that. So that is the acceleration. Let me do the next one. If the thing is falling, it's actually going downwards like that, then what is happening to the force acting on it? Well, again, it is acting downwards. Therefore, it is going to be accelerating downwards like that. Okay, it is still acting downwards. The acceleration is downwards. So what happens if it goes in a weirdo direction like the third one? Well, I'm not bothered because it has got a weight which is acting downwards like that. Therefore, it will accelerate downwards. Now we can go back. Let me just do that. There is my acceleration. Now, I am not going to, and you cannot make me do a vector sum with those diagrams. You can't do that because they are different quantities. The velocity and the accelerations are different quantities. That's super important. So I cannot add them because you can't add a velocity to an acceleration. It's meaningless. It is bonkers. But what it does mean is if I now draw this little thing over here, if I draw this triangle like this, it does mean that my acceleration is going to change. So I've now done the components of the red velocity. the acceleration is acting downwards, therefore it is going to affect the vertical velocity because the acceleration is acting in that direction because Newton said so for a second time. This one here, that velocity, the horizontal component of the velocity, is going to remain constant. Why? I hear you say in unison, because there is no component of the acceleration in the horizontal direction. And that's the answer that the examiner wants to see. Okay, there is no component of the body's weight in the horizontal direction. Now, you probably realize that because all the way through this, what I've been doing is intermittently putting that slide in. That I want to get inside your heads, because that's what you need to know. If there is no component of a body's weight acting horizontally, then it will not accelerate horizontally. And if it does not accelerate horizontally, then its horizontal velocity does not change. That's all pointing things on a diagram and stuff. That doesn't convince you, I can tell. This thing might. This thing might. So I'm hoping that you've seen this, or you will see it, or you understand it nearly, because I hope in about 5 minutes you will understand it completely. We have got a little thing. It's about that big, maybe about the size of a calculator, like that. And there is a spring over here which pulls that downwards with a force F like that. Okay, there is a little catch, there it is, which catches this black thing in that position. So there's a pivot there, you pull it back, it goes ba-ding there, and it holds it in position. The spring is in tension. It is trying to make that thing rotate about there. Okay, so that's what the thing does. Now, there are two balls strategically balanced on this thing. Ball A over there is simply, this thing's a bit of 90-degree angle iron. So when this button is pressed and that is pushed down and that goes bedoing like that and that goes bedoing like that and the whole thing boom, spins really quickly, you can see, I hope, that that bit of metal is going to just go that way very, very quickly. The ball, with its inertia, stays in the same place. But all of a sudden, it sees that there's nothing holding it up. It's there, it's an empty space. There is nothing holding it up. Okay, that's ball A. Ball B on the other hand, you can see, I hope, because this thing goes bedoinging like that, that vertical bit of metal oof, hits ball B horizontally and fires it horizontally at exactly the same time from the same height. So B gets an initial horizontal velocity, A does not. They are both at the same height, and then something interesting happens. So, because I'm very short, I always had to stand on a stool, don't care about health and safety, holding the thing up like that. Okay, luckily the room I was in had very high ceilings, so I could stand on a stool, on a desk, holding up above my head. There are the two balls like that. So, the question is, which ball hits the ground first? Obviously, if somebody was walking past and I would get them in, I'd say, what A levels are you doing then? Say maths, French, and English. I'd say, brilliant. Which of these balls is going to hit the ground at the same time? They'd look at me as if I'm an idiot. Then they'd say, well, obviously, it's the ball that you fire horizontally because it's got further to go. Therefore, the one that falls vertically is going to hit the ground first, and then the other one and hits the ground later. Thank you very much. Thank you very much. But what that person didn't realize is that there is no component of the body weight, therefore it will not accelerate horizontally. And as a result, you've got to consider the vertical and horizontal motions independently. Okay, the vertical one has got nothing whatsoever to do with the horizontal component of its velocity or its displacement. You've got to do them completely separately. So if I just go back to that, This one, I'm not going to draw this very well. This one is going to go, let me draw with the ruler because it's going to go vertically downwards. That goes poof like that, and goes blink and hits the ground like that. But much to everybody's surprise, especially the person doing French, English, and German or something, poof, hey, that's good. Oh, that was good. Oh, I've never done it that well before. So that hits the ground there. Now, weirdly, they both hit the ground at the same time. That is important. The reason is this one on the left is going vertically like that and accelerates vertically. This one on the right also accelerates downwards at the same acceleration. So since they're at the same height, they are going to hit the ground at the same time. So that is the fundamental thing. They both hit the ground at the same time. And what happens to the horizontal velocity is completely irrelevant. It doesn't matter. Now, what I've done is that. Okay? So that's what's going on. Okay? We are going to think about the position of this thing. Now, what I did is I used those equations. Okay? This one up here, the GCSE one, there, distance is velocity times time. I'm going to just remind you that the horizontal distance is the horizontal velocity times the time. That's important. The horizontal velocity times the time is its horizontal displacement. Now, what's going on with its displacement in this direction is irritating because you've got to use one of these equations of motion because it is accelerating. Okay, it is accelerating, and that means that v and u are not going to be the same. So it is accelerating. So you've got to apply these equations to find out where it is vertically, and that's GCSE one when you are thinking about the horizontal displacement. So let's have a go. So there it starts like that. Horizontally, it goes the same distance in the same interval of time because there is no component of its weight in the horizontal direction. That's how you get the mark. However, what it's doing vertically is in the first interval of time, it falls that much. And in that time, it has accelerated a bit. So it is going faster. Therefore, in the next equal interval of time, it's going to travel further. And in the next equal interval of time, it's traveled further still, and further still, and further still. So that is its vertical displacement. We've thought about its horizontal displacement. So what does the ball actually do? Well, it actually does that. That's what the ball does in equal steps in time. I'll go through it again. It goes in equal directions, distances horizontally. Those lines are equally spaced, but vertically it falls more and more and more. So how Peter Lord knew that? Well, he didn't know it. He just intuitively knows it when he does his throwing things about in Shaun the Sheep and all his Aardman, what are they called? Wallace and Gromit films. He just knows. His animators just know because they are eye-wateringly geniuses. Anyway, let's have a think about the three things going on. So here it is. Time equals 0. It is there. What is its displacement after equal intervals of time? Well, the first interval of time, that is its displacement, then that, and then that, and then, sorry, this is a bit messy at the top, and then that, and then that. That is the displacement, okay? And we're going to see how we can work out that particular vector later on, right? That is how far it's gone from the initial position. But now let's look at its velocity. Oh, poops, this is difficult. The velocity is a vector. Okay, so we will be told always, nearly, that what the horizontal velocity is. So I'm going to do it here. I'm going to do it there. So let's say that is the horizontal velocity. That, by the way, stays the same all the way down. That is the same all the way down. Why? Because there is no component of its weight in the horizontal direction. So its horizontal velocity stays the same. I'm trying to draw those the same length. The vertical velocity, as we saw, does not. That changes. So how does it change? I need an equation. I'm looking at that box down there. It's not that one. That's a GCSE one. It's not that because it is accelerating. I want to know its velocity after a certain time. I'm going to go for that one. There we go. Now, with that formula, I can calculate what its vertical velocity is. So I'm going to do it on this one. Let's say it's that. I made it up. It's something like that. Okay. I'm not Peter Lord. I'd have to calculate it. So that is its horizontal velocity. That is its vertical velocity like that. I calculate it from that. Now, the important thing is to know what those symbols mean. V is the vertical velocity. I'm thinking about the vertical component now. That is equal to V equals. What is U? It's the initial velocity, but the initial vertical velocity. What is it? The moment I let go of this thing, its initial vertical velocity, even if I throw it, and I'm going to, even if I throw it horizontally, the initial vertical velocity is 0. Therefore, U goes. So now I've got V equals the acceleration times time. Hold on, why does it look like that? Like that. So V equals the acceleration times time. Now we know that the acceleration is the acceleration due to gravity, but you've got to be super careful on that because it is traveling downwards. It is going downwards. So G, the acceleration due to gravity, is downwards 9.8. It's minus 9.8 T. So whatever T is, if these are taken every 1 second, 1, 2, 3, 4, T is 4 seconds. They might be taking every 10th of a second, 0.1, 0.2, 0.3, 0.4 seconds, or whatever. They will tell you. Okay, so you have now got your two velocities, your horizontal one, easy, your vertical one, slightly tricky. But notice that the vertical velocity is going downwards. Then to find the resultant velocity, then what you have to do is work out that using probably a cheeky little bit of Pythagoras, if you like. So that is the square root of VH squared, Pythagoras. They also would like, because velocity, this is difficult, isn't it? Because velocity is a vector, we want a direction. We've got magnitude, it's a vector, we need direction. So on my diagram, I'm going to say at an angle of theta to the horizontal. You could say at an angle of phi to the vertical, if you like. It doesn't matter. You've just got to show that you have shown which direction the velocity is traveling in. Let's do it. So if I just draw a triangle here, we can see that theta is, there we go, theta is, well, I'm going to say tan theta. Tan theta equals opposite, which is that, VV over VH, opposite over adjacent. There we go. So we can quite easily, remembering our trig, work out the angle that it travels at. So the velocity, there's a lot going on there. Bit of a pain. Hold on. Let's go back. Let's go back. Displacement. Actually, displacement ain't that easy neither, because that displacement in that direction, S horizontal equals V horizontal times time, because that's GCSE, because it's not accelerating. Hold on, hold on, hold on, hold on, hold on. This distance here is that. This distance here, the distance it has fallen, we need to use one of the SUVAT equations. I'm just going to flash them on the screen. There they are. So we need to know how far it's traveled. It's that one. There it is. Let's use that one to find out how far it has fallen, to find its displacement. Again, the initial vertical velocity u is 0. So that distance there, the vertical distance, is a half a t squared. Almost. A is negative, the acceleration due to gravity, so is that, because S is below where it started from. Okay, so that is quite tricky, actually. That's quite tricky. The easy one is that one, because I don't mind where it is. The acceleration is always downwards, because we are ignoring air resistance. The acceleration of this thing is always downwards like that, and it is minus 9.8 meters per second squared. Don't mind where it is. The acceleration is the weight of this thing, which is always acting downwards. So acceleration is easy. Okay, quite a few questions. There's one coming up. We might have time if we get there. Simply says, draw on the trajectory, the an arrow to show the acceleration at point X, downwards. Okay, downwards. Nothing strange going on there. Now, let's have a look while we're here at a multiple choice question. Okay, so that's it. Okay, so you would expect that to be like the demonstration that you've probably seen your teacher do. And you're expecting the question, which one lands first? None of them. The correct answer is they all land at the same time. But this is slightly harder than that. These are the options. Okay, so it's a variation on a theme, so it's slightly different. We know that they all hit the ground at the same time. So it can't be that one, and it can't be that one. Now we've got a slight issue. We got to think about the speed. Which one hits the ground with the greatest speed? Well, if you think of your vectors, we've got, let's do D first. U is going to hit the ground like that. W is going to hit the ground with the same vertical velocity. Okay, because the vertical directions are the same, because we don't mind about the horizontal directions. But W started off with a horizontal, there it is, a horizontal velocity, which stays the same. So there has got a V horizontal. That gives us a resultant vectory thing like that. Now, because Pythagoras said so, that resultant of that is going to be bigger than that. That is your answer. Okay, quite a variation on the theme, quite tricky. Right, as I said, that. Okay, upwards is positive, therefore the acceleration is always negative, which is downwards. So it doesn't matter if the ball is initially stationary, initially going up, initially going down, initially going at an angle like that. It doesn't matter. We've got to, when we apply those SUVAT equations, we got to be really careful that we know and stick to our convention. And usually, well, yeah, I'm going to say for SUVAT equations for projectile motions, stick to that convention. Upwards is positive. So if a ball is thrown upwards at 25 meters per second, then the initial vertical velocity, uv, is plus 25 meters per second. If the ball is thrown downwards at 10 meters per second, then vertical, uv, is minus 10 meters per second. Okay, make sure you use your convention and stick to it, which means that the acceleration due to gravity is going to be minus 9.8. Oh, stop. Whoa. Oh, bad. Okay, sorry. I'm going to change that. I just added that about an hour ago. Oops, I got that wrong. Don't tell me I got it wrong. I can see that I got it wrong. I'm not going to explain. I'm just going to apologize. I'm sorry for that. That's bad. Right. Let's have a look at what the trajectory actually looks like if we start throwing objects about. So I'm going to get to the fence simulations. I'm going to do that one. Okay, what we can do is we can start with our ball there and we can adjust its initial height. That's not particularly interesting. Its initial speed, quite interesting. The angle, very interesting. Don't mind about the mass, and we're obviously going to stick to being on the Earth. Right, but look, we can look at our positions, our velocities, and our accelerations, and our forces. So we can draw, the computer is going to do it for me. The computer is going to work out what's going on. So let's have a go at our Fent simulations. Good old Walter. I wrote to him once and said, these are brilliant, Walter. He said, thank you very much. There it is, projectile motion there. Boof, ding, there we go. Right, so let's have a look at this. I'm going to do a simple one. I'm going to start it at an angle of 0. There we go. Okay, like that. I'm going to make it go at a speed of 5 meters per second. There it is. Yeah, 5. Leave it at that. Okay. When I press start, there it goes. That is what it looks like. This trajectory looks like if I do it from a height of 5 meters. Let me just change that to 10. You can see what it does. Reset. 10. Boof. Boof. Right. Boof. There we go. It kind of does the same thing. Slightly boring. I'm going to reset it. I'm going to change the speed to 20 meters per second. Start. Wait a minute. I just want to make it look good. Reset 20 meters. Let's do it at 25 meters per second like that. There we go. Start. Oh, he's changing my. Oh, darn it. He's changed my scales. Doesn't really matter. Oh, man. Let me just refresh that. There we go. I prefer that. I shouldn't have messed about. I'm going to start with that, but change the angle. There we go. Right. That's what it looks like. You can see the position. That is that red line. Okay, now what the computer is doing, it is calculating the velocity, the horizontal, distance and the vertical distance and increasing that line. That's what it looks like. If I want the velocity, here we go. Watch this. If I reset it, first thing, can you please keep your eye, I'm going to do it in slow motion, can you keep your eye on the horizontal velocity? It stays the same. Horizontal velocity stays the same, but because it is accelerating vertically, the vertical velocity starts small, gets bigger and bigger and bigger because it is accelerating in the vertical direction, because that is where the force is acting and there is no component of that force in that direction. Okay, I'm going to reset it and I'm going to just do this at 30 degrees because that is like one of our exam questions. Okay, something is going to be projected off a cliff at an angle to the vertical like that. Now we're going to have to think about what's going on to answer the rather tricky questions. I haven't shown you the acceleration yet. Reset. Acceleration. Very boring. Very, 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 very boring. Because the acceleration acts downwards and does not change size. Okay? So lots of multiple choice questions about those, where they're talking about vectors, position vector, velocity vector, or acceleration vector. The force, as you know, is the F equals ma. So if I just reset it, not in slow motion, takes forever. There we go. The force remains constant like that. Quite nice. Now let's work out how it did that. How did it actually do that? Well, you know, because your teacher banged on about it a million times, and so have I, you are going to have to be able to use a spreadsheet. Now, I know, some of you love spreadsheets. Like I guarantee whatever job you're going to do, anything you're going to do, in 5, 6, 7, 10 years or whatever, you are going to be writing spreadsheets like there's no tomorrow. It's worth starting now. If you haven't already written a spreadsheet, have a go at writing one. This is quite a simple-ish one that I wrote. Okay, it mimics what we just saw. Okay, I'm going to go back to the right slide like that. I'm going to just set my variables. So what I've got is I have got a ball being projected from a height of 14 meters at an initial horizontal velocity of 15 meters per second. Okay, that's what I've got. Now, just to give you a little clue, that little caret sign there is per. Okay, so when you square something, you do caret, which is shift 6. 2, that squares it. That's what Excel thinks. That's what you do that for Excel, and it knows that you're squaring it. So let's have a look at my my equations, my formulae. So here we go. There are my formulae. Okay, for the time, I just started by saying the time increases in equal steps like that. Every 10th of a second, I want to know what's going on. You can do whatever you like. Here, I've calculated the horizontal velocity. Now, the horizontal distance is the horizontal velocity multiplied by the time, and it stays constant because that's GCSE. So there is my formula. There is my formula for the horizontal displacement. It is. So A2. So that's working out that formula there. It says start off with equal sign. Got to start off with an equal sign to say that is a formula. Excel, I'm writing a formula. Equal sign. It means anything in cell A2, there it is, multiplied by, so that, let me just rub that out, multiplied by, so the, what's it called, asterisk, is multiplied by 2, multiplied by 2. That's nice. Yep, that's it. So that is my equation. Now, what I did was let me go back. I'll show you my spreadsheet. The tricky one is the vertical displacement. Now, the vertical displacement is starting at 18. Okay, so I'm starting 18 meters high, minus, because it's going downwards, the distance, which I calculate, my displacement, sorry, I calculate from that, which is from the formula S equals ut plus a half at squared. U, the initial vertical velocity, is 0, so I don't care about that. All I'm trying to find is 18, the initial, minus the displacement, 0.5 times the acceleration times t squared. So there's my 0.5 times the acceleration times the time, cell A2, caret 2 squared. Well, that's my spreadsheet. Okay, let's have a look at the actual thing because it is here. There it is. So, did I change? I slightly changed it. That's why I hesitated when I saw that too. Because I have changed my velocity, my horizontal velocity to, where's my annotations gone? There they are. I'm going to rub out all that stuff. So I've changed my horizontal velocity to 15, but I can change it to anything I like. So I've put my horizontal velocity into cell F3. I've put my height in cell F2. Now, something that they have asked, and I thought it was unfair, but I'm telling you now, is when you do a formula, sometimes you use the dollar sign. So there you can see, unfortunately, it doesn't expand the formula, but the formula to calculate B3 is A3 times dollar F dollar 3. Now that means that the dollar F means it's always in column F, and the dollar 3 means it's always in row 3. It is always F3. So when you copy the formula down, as you do like that, it stays at F3. It doesn't move it as you go down. You will write a spreadsheet and you will find out what I mean when you use the dollar notation. It is super, super important. Anyway, there is my trajectory. It works. Okay, so there's the trajectory. I suggest you have a little play with Excel. That's quite a nice one to start with because it's got the squared in it, it's got the carries, it's got the pluses, it's got the negatives. And when you plot the graph of vertical displacement against horizontal displacement, lo and behold, it gives a realistic Wallace and Gromit trajectory. Okay, because Peter Lord can do spreadsheets in his head. Right, let me get rid of that. Let's move on. Let's move on. So there's my trajectory. Here's an exam question. Okay, so maybe knowing how Excel works will help you with this exam question because it's exactly the same thing. So here is something launched from a height of, from 1.4. I have to work it out there. 1.4. It's going downwards, look. And it travels a certain horizontal distance. It tells you in the question how often the photo is being taken. Okay, so you can work out the velocities and you can work out the horizontal velocity. If they don't do that, if they have a sense of humor, you can work out the horizontal velocity from this. So I don't know if you've done this experiment, but what we're doing is rolling a marble down a ramp, and we assume incorrectly that all the gravitational potential energy of this thing as it falls a distance capital H is its kinetic energy here. We are assuming that it is all converted to kinetic energy. So that means that mgh equals a half mv squared. M's cancel out, and v equals the square root of 2gh. There we go. So that is the horizontal velocity when it leaves the ramp. However, it is its initial horizontal velocity like that. That is where it leaves the ramp. Then what it does, it launches off the edge of your desk into space and it lands somewhere there. Now, usually the question says, what is the range? In other words, where does it land out there? Okay, that is what you usually have to calculate. Or if it's not one of them, it could be a different scenario, which is an electron going through an electric field. Like I did that because some of you have started electric fields, and exactly the same thing. Over here, the electron is traveling at a certain velocity like that you calculate from the accelerating voltage. When it gets into the electric field, it experiences a force in the direction of the field lines, because that's what they are. We're going in the opposite direction, because electron's negative, like that. So wherever it is, it experiences a force downwards like that. So the shape of that trajectory is the same as the trajectory of a ball, cannonball, if you like, being fired horizontally from the top of a castle. Okay. I chose this because it goes through what you nearly have to do every single time. Okay. So we're going to do this question. Oh, okay. Okay, so that's what we've got. They've put the figures on the diagram as well. Now, first thing we have to do is that. Ooh, boy. Oh, good. Assume air resistance was negligible. That was nice. So we've got to go back to remembering me on the stool, on the desk, chucking balls all over the lab. And we know that this is the important thing. It takes the same length of time to go from there to there as it does to go from there along the parabolic path to there. Too complicated. Let's do the blue one. Okay, it's the same time. So, we need to know how long it takes to fall 67 meters. So let me do this. We know S, we know A, the acceleration due to gravity. We want to know T like that. We know the initial velocity like that. How do we find it? Stare at those for a minute. In fact, stare at them for about 1 nanosecond, and that springs to mind. Right? That is the formula like that. Okay? But this is going to be projectile motion. So we've got to be super, super precise. We know that the initial velocity, vertical velocity, is 0. So we can forget about that. We're only thinking about the vertical component. Okay? So we've got S. How far does it go? Well, it goes 67 meters downwards equals a half. The acceleration due to gravity is 9.8 downwards. So it's half times 9.8 times t squared. So you solve that. A nice quadratic, you don't have to mess about with the formula. So you get a number. Don't know what it is. Oh, okay, there we go. It's going to be something like 3.7. I'm not going to waste your time now because it will be. So t equals about, okay, 3.7 seconds. Thank you very much. 1 mark. Done it. So now we know it takes 3.7 seconds to hit the ground, the blue one. It also takes 3.7 seconds to go the pink one from the top of the castle to almost hitting the ship. Nobody got hurt. Nobody got hurt. So let's have a look at the next question. And much to your surprise, it is that. Calculate the velocity at which the cannonball was fired. Well, that is the distance it goes in 3.7 seconds. And we know that the horizontal velocity, which is what we're trying to find, remains constant. So it doesn't matter that it's down 67 meters. Not in the slightest bit bothered. We know, because we did GCSE, that velocity is distance over time. So now it is not accelerating because we're talking about the horizontal displacement and there is no component of the vertical acceleration in the horizontal direction. Same old thing. So what we're trying to find out, the velocity is distance 150 divided by 3.7 equals whatever it is. And I shall get the units right this time. Okay, quite good. Oh, I've just seen another part of the question. Oh, yes. Oh, yes. The last part of the question, I think, is that. No, there's another one. Okay. The part before, we got a value for the... we got a value for the horizontal velocity. I don't know what it is, but we got a value. I can't be bothered. We got a value for that. So that is our horizontal velocity, 150 divided by 3.7. We need to know what the vertical velocity is. What is its vertical velocity? Because you can see that it is traveling at an angle like that. So that's what we want. Oh, sorry. All we want is the vertical component. Couldn't care less about the horizontal yet. I just looked at the next question. So the vertical component, what do? We know how long it's in the air for. We know the acceleration. We know the initial velocity. Job done. It's that one. V equals U plus AT is the equation. But we want V, the vertical velocity. The initial vertical velocity is 0. The initial horizontal velocity is not 0, but the initial vertical velocity is 0 minus 9.8 times 3.7. 3.7. There we go. In your calculators, you get a value for the vertical velocity to be negative because it's going downwards. Right. The last question is that. Come on. That. By calculation or scale drawing. Okay. So I'm going to do both. I'm going to do both. So we've got both values like this. Boom. So that is our thing there. So by calculation, we're going to find the magnitude of that thing. Well, we know what VV is. We know what VH is and what VV is, the horizontal velocity and the vertical velocity. So we can do a bit of Pythagoras to find out what the magnitude is of the resultant from that vector triangle. But we want the direction. So what should we do? Let's do that. I'm going to find that angle there, theta there, which is inverse tangent that divided by that. Nice. Okay. Scale drawing, though. Scale drawing. There will be a lot of space for this. So I'm going to make these numbers up. Let's say that is 14 meters per second, and this is 19 meters per second. Made that up. Okay. To do a scale drawing, what you do is exactly the same thing. You draw a triangle. No, you don't. You draw the two velocities like that. This one, you choose a scale. I'm going to do 14 centimeters, and this is 19 centimeters, so that it fits on an A4 sheet of paper. You can do 7 centimeters and 9.5 if you like. It doesn't matter. It's got to be to scale. Then with your ruler, so I'm going to do this badly. With your ruler, you draw a line. So that is parallel to that, and another line like that. So that is parallel to that. And then you draw the resultant, which is from there down to there. You measure it with your ruler and you convert it back to velocity using whichever scale you chose. And you get your protractor out and you measure this angle to find the angle to the horizontal. And that is your magnitude and direction. So quite a tricky little thing there. Quite a tricky thing.